The goal of exercise 6 in chapter 14 is to implement the Moore-Penrose pseudo-inverse algorithm based on the description that I provided in this chapter. Now, you already know, and you have been using this function here, pinv, numpy.linalg.pinv, to compute the Moore-Penrose pseudo-inverse. But so far in previous chapters, I haven't really explained exactly how that algorithm works. But in this chapter, I did explain how that algorithm works. So what I want you to do here is create your own code, write your own algorithm without looking at how NumPy implements it. You just do it on your own to compute the Moore-Penrose pseudo-inverse. Now, the only tricky part is that you have to keep in mind that there can be singular values that are effectively zero. These really are zero-valued singular values, but because of rounding error and just computer discretization, the empirical singular value ends up being something like 10 to the minus 14 or something. So you need to figure out a way to deal with that. Okay, so then test your code on a 5 by 5 rank 3 matrix. So create a 5 by 5 rank 3 matrix. Now, this is a singular matrix. It is not invertible. If you take its SVD, it will have 3 non-zero singular values and 2 singular values that in theory should be exactly 0. And in practice, they might not be exactly 0, but they might be just really, really tiny. Okay, so let's see. So create your own function to implement the pseudo-inverse, and then take the NumPy's implementation of the pseudo-inverse and on the same matrix to compare your result to NumPy's result. And finally, the very last thing to do here is to open up the source code for numpy.linalg.pinv and check out its implementation. So here I create a reduced rank matrix. So this is going to be a 5 by 5 matrix with rank 3. And actually, I'm going to first comment out all of this stuff. So I just want to explore this matrix for a little bit and its SVD. So we can see, let's see, the matrix A looks like a bunch of random numbers. The precision is so high here, it would be absolutely impossible to determine the rank of this matrix just by looking at it. But let's see what its rank is. So linalg.matrix rank. So NumPy says that it has a rank of 3, no surprise. And let's see what its singular values are. So S. Now you can see 0 of these values are actually equal to 0, right? So you might have expected, this is 4, this is 2.5, this is, something small, this is 0.5. And now here, these two numbers in theory should be exactly 0, but they're not. They are non-zero numbers, even though this is a rank 3 matrix. So when you implement the pseudo-inverse calculation, you need to account for this. You do not want to invert these singular values. In fact, the inverse of these would be ginormous. You can see how absolutely mammoth these numbers are going to be, right? This is this is like the number of stars in the Milky Way galaxy is somewhere around here. All right, so now let me uncomment this. Okay, so I'm going to talk about this I'll talk about it now. Okay, so there's different ways to specify the tolerance. You can say something like, 10 to the minus 15 or 10 to the minus 14, just fix it to a particular number. What I do here is set it to be epsilon, so EPS. This is the computer epsilon, that is basically the smallest distance between two floating point numbers that NumPy can represent given this hardware. And this is the hardware of the Colab server that we are attached to. It's not the hardware of my computer. And then I scale it up according to the larger of the number of columns or the number of rows in A. So this is a fairly dynamic tolerance, because when A gets bigger, then the tolerance also gets bigger. So for huge matrix A, it's going to be larger, higher risk of rounding errors, just because larger matrices involve a lot more flops, a lot more computations. And so, yeah, so this increases the tolerance the larger the matrix gets. Okay, so that's our tolerance. It's going to be some small value. And now actually I'll also show you what tall is. So don't don't pay too much attention to this. I just want to show you this number. Okay, so this is around 10 to the minus 15 in this case. Okay, so here I create a vector sinv, and you can see now if I would just get rid of this, here I'm literally just reciprocating the singular values. This is what you would do for the full inverse. So to compute the full inverse of a matrix that is invertible, this is what you do. You just literally invert all of the singular values. And the idea of the pseudo-inverse is to invert the singular values, but only the non-zero singular values. Now, again, in theory, the theory of linear algebra tells us that we just need to write it like this. We just say any singular value that is larger than 0. Of course, I just showed you the problem with that simple theory-based approach. So instead, we say larger than tolerance, which, yeah, as you see here, is larger than around 10 to the minus 15. Okay, so that is like the hard part. From here, all we have to do is multiply out these matrices. So V times sigma times U transpose. And this is a little confusing, but I've already mentioned it multiple times in past several of these videos. Python spits out V transpose. So you actually want matrix V, you have to transpose V transpose. So, okay, so that is my algorithm for the pseudo inverse. And here is the output of pinv. And yeah, here you see that those are the same. So we get the same result as what NumPy is returning. Okay, and then the last thing I want to do in this video is inspect the source code for pinv. I'm not sure why this functionality isn't working, and then I had to restart Colab. So anyway, we can also open the source code like this with 2 question marks after the function name. And yeah, so here we see the source code for linalg.pinv. And what I want to do is scroll down to the bottom past all the docstring, help file stuff, references, etc., etc. And here's an example. And let's see. Okay, so the input to this function is variable a, which is a matrix, a NumPy array. And here, let's see. So I'm just going to point out a couple of the key lines. I'm not going to explain every single line. Here, NumPy takes the SVD of matrix A. You can see it adds the optional input full matrices equals false. This is an input that we explored in the beginning of this chapter. I believe it was exercise 1. So here we get U and V transpose, and then the sigmas in the middle. So now what do we do? So, or what does NumPy do? So NumPy divides 1 by s. So this is 1 over 1 over s, so 1 divided by the sigmas. And then you can see that, I'll get back to this in a moment. Here we get the result. This is the output of the function, and it is the matrix multiplication of the transpose of V transpose, so that is V, times the S matrix. And here this is just expanding this out to a matrix, so it goes from a vector of singular values to a matrix of a diagonal matrix of singular values. And then we have U transpose over here. Okay, so then we get to this couple of lines here, and essentially this code is computing a cutoff threshold. This is what I call the tolerance, based on the size of the matrix times the matrix condition number, and then any singular values that are smaller than that matrix are set to 0. To be honest, this code is a little confusing, and actually this implementation is different from what it was when I wrote the book, which wasn't that long ago. So it looks like they've changed something in their code. Maybe this is a more numerically stable method of doing it, but the exact implementation isn't so important. Different developers, different coders will implement things in slightly different ways based on a variety of factors. The important thing is that you can look at some source code and understand the general principles, even if it's slightly different from how you or I would implement it, you understand the principles based on your knowledge of linear algebra that I hope you got from this book.